All right, everybody, thank you for joining. This, again, is a webinar showcasing a live ETH2 workshop featuring the Whiteblock Genesis platform. Again, if you have any questions, please feel free to just go to the chat, ask a question, participate with the audience. Trent is here to organize those questions, help you get situated, and we'll have plenty of time for Q&A at the end. We'll make sure of that. So make yourself comfortable, and we're going to get started right away. So today joining me, with the pleasure of introducing to you guys Vitalik Buterin, founder of Ethereum and researcher on Ethereum too, Preston Von Loop, who's working on Prism as part of Prysmatic Labs, Jay Mulzer from PegaSys, working on the Artemis client, and myself, Antoine, from Whiteblock. We have a packed agenda today, so we're going to talk about a few things. We're going to first discuss the Genesis platform, just introduce you where we're coming from in terms of distributed systems testing. Then Vitalik will take us on a tour of Ethereum in Ethereum 2.0. We're going to have some time for Preston and Jem to introduce themselves, their team, the effort they're involved in, the client that they're working on. We'll talk a little bit about the challenges that are ahead of us and that we're working on right now in terms of interoperability for networking. We'll do a short demo on the Whiteblock Genesis platform to showcase how we can manipulate network conditions to make things happen. And we'll have then plenty of time for Q&A. We have already some questions and topics that popped up in the chat. Let's make sure we get time for that. So just going to take 5 minutes of your time, and we're going to talk a little bit about the Whiteblock Genesis platform. So Whiteblock Genesis has been around for 18 months. We are an end-to-end testing and development platform for distributed systems. We are being leveraged by ETH2.0 implementers, so they can actually test their testnets in isolation and make sure that everything works. We're still used by distributed systems in general, IoT, other blockchains. Genesis platform has a comprehensive set of features. We have the ability to offer granular control over every one of the nodes in your network, running them into a different VLAN for each of them. We can control bandwidth, latency, network blackouts between all nodes or just one network connection. We're protocol agnostic. We support over 20 different blockchain protocols, including, of course, Ethereum and Ethereum 2.0, allowing to reuse and leverage the unique functionalities of those chains so that we can get the data, we can actually analyze what's going on. Talking about analyzing, we have powerful analytics bundled in, so we give you access to your data, your block data, your log data. We make it available to you so you can work with it with data science tools, which are best in breed on the market today, such as Jupyter Notebooks. All this comes fully automated. In less than 30 seconds, you can set up a testnet, you can get it going, you can automate that as part of your CI/CD pipeline, and everything works well with your existing tooling, so you can just wish away all your complex testing and is just going to happen automatically going forward. The way we interface with developers today is using a command line interface that allows you to control, command individual nodes, configuring a set of advanced tests and observe them performance in real time. Also comes with a complete SDK and API, so people can integrate that into Jenkins or Circle CI, Concourse, all those test suites that exist today. All right, so just sum up, so we know about this a little bit. So Whiteblock Genesis is the all-in-one testing platform for blockchain and distributed systems. Very helpful for any Web3 application, be it if you're a dApp developer, a protocol developer, or if you're just looking at a very complex deployment with many moving pieces. We offer for you a robust test suite that you can use for any type of integration with your CI/CD pipeline. Every stage of the lifecycle of your platform, we can help you. We can help you from the point of view of simple development and staging, prototyping, proofing, benchmarking, to the point of running migrations, upgrades, hard forks, and making sure that you don't see performance degradation between releases. This is what we can help you with. So we're going to see how this plays into Ethereum. I'm going to invite our next speaker, Vitalik, to talk a little bit about Ethereum and Ethereum 2. Vitalik, are you with us?
Yes, hello. Can you all hear me?
I can hear you.
Okay, excellent. So I guess I'll start off by just giving a general kind of overview into what Ethereum 2.0 is and kind of where we're at right now progress-wise. So the basic idea behind Ethereum 2.0 is that it's this major upgrade to Ethereum whose two flagship features are number one, Casper, a proof-of-stake algorithm, which is intended to replace the current proof-of-work mechanism. And number two, sharding, which is the scalability technology that basically says, instead of every computer needing to verify every transaction, we just have every transaction be verified by a small random subset of all of the participants or all of the validators in the network. So Ethereum 2.0 is the specification. There is a specification that we've been working on, and at github.com/Ethereum/ETH 2.0-specs, if someone wants to put the URL wherever people see it. There's the specifications of what we've been developing so far. But in general, ETH 2.0 has been split up broadly into 4 phases. The first phase that we call phase 0 is basically creating a proof of stake chain. So using Casper FFG plus LMD Ghost, that's the proof of stake algorithm that we've been working on for a few years. That's been inspired by a traditional Byzantine fault tolerance theory, and some traditional proof of stake has this concept of economic finality. And phase 0 is just that without any ability to process transactions, right? So phase 0 is basically just about creating this proof of stake chain that can just have a chain and keep the chain growing and allow people to deposit Ether from the Ethereum 1 network into this new Ethereum 2 chain, and basically just kind of get the thing running. Phase 1 after that is when we plan to add shards and data on shards. So the way that shards work is that there's 1,024 different shards, each of which you can think of as being kind of like sub-blockchains. So they're blockchains, but they're not quite independent because they depend on this kind of central beacon chain that we're launching in phase 0 for their consensus, and that they also have talk with the beacon chain. And on each of these 1,024 shard chains, there will be on average 16 kilobytes of space every block, but the block size could go up to 64 kilobytes where you can publish data. And in phase 1 by itself, the data doesn't mean anything. But the idea here is to basically have all of the infrastructure for actually managing a sharded blockchain kind of running in its full form, right? So if you are a validator, so if you're someone who deposited Ether, then in phase 0, you'll just be signing blocks and maintaining the chain. In phase 1, you will also have this responsibility to be verifying blocks on a random shard that you get assigned to, and you get frequently reassigned between different shards. And you'll have to verify these blocks, create blocks on shards, and sign off on attestations that contain pointers to those blocks to basically link those blocks up to the beacon chain. So in phase 1, like basically there will be data scalability, and at current proposed numbers, the Ethereum blockchain will be able to process about 5 megabytes per second of data, which is about 500 times or 500 to 600 times more than the theoretical maximum right now. But it will not be able to process like smart contracts or any kind of code execution yet. In phase 2, we will be adding basically the ability to have code executed on chain and to have Ether actually be controlled by that code. And we're doing it through this mechanism called execution environments, where basically there exist these kind of bottom level smart contracts on the beacon chain that hold ETH and that implement internal logic, where parts of that internal logic get executed on shard chains. And on top of those systems, you can emulate things like a scalable version of the existing Ethereum system, among other things. So at phase 2, you will basically be able to do scalably what you're able to do with Ethereum now. And then phase 3 is any improvements that we want to do after phase 2. So this could include increasing use of Starks for security. This could include switching from Casper FFG to Casper CBC. Yes, I said 5 megabytes a second. The way I got that number is 16 kilobytes divided by 3 seconds and multiplied by 1,024 shards. I mean, still subjects to change depending on what networking kind of people end up saying and what tests ends up revealing, but that's kind of the goal at this point. So in phase 3, things like CBC, things like adding in Starks, just generally improving the efficiency of the system. If we discover any improvements, then we'll add them in, and it keeps on going from there. So it is possible that after phase 3, that we're not really going to need any more kind of fundamental changes to the Ethereum chain structure, and it will be possible to do pretty much anything that we want to do on top of just this kind of quadratic sharded system and layer 2s and the execution environments that get built on top of it. So at least one of my own personal goals is to try to set up the system so that after all of these phases get fully implemented, there isn't really much need for a continued rejuggling of the base layer, and most of the innovation can happen through these execution environments. I know there have been some presentations about how these execution environments work publicly, but I maybe don't want to go into too deeply because we don't have infinite time here. So that's basically the roadmap. In terms of actual progress, the phase 0 spec has been frozen. There's a lot of people hard at work on nailing down implementation of phase 0, getting clients to talk to each other, figuring out how all the networking is going to work at scale. Phase 1, the spec is in the process of being nailed down. And it's there's people starting to look at implementing it. Though in terms of, like, spec-wise, phase 1 is still considerably smaller than phase 0. So the bulk of the complexity of phase 1, I think, will basically be just managing this idea that you have data flying around in different shards and clients that have to talk to different shards, and not every node is receiving every transaction. And then for phase 2, there's a lot of kind of current ongoing research and thinking around how concretely what execution environments could concretely be built and how they would work. Yeah, and if there's anything specific people want me to talk about, I'm happy to. I mean, otherwise, happy for other people to talk as well.
Yeah, absolutely, Vitalik. Thank you so much for this overview. We'll get to questions at the end, so if any questions, we'll be able to take that at the time. I'm going to move on to our next speaker, Jem, who's going to talk a little bit about one of the clients that is working on the Ethereum 2 specification right now. Jem, are you here?
Yep. Can you guys hear me?
Yes.
Perfect. So before I talk about like Artemis, our Ethereum 2.0 client, I want to talk a bit about like PegaSys, the company behind Artemis. If we can move to the next slide. So the main goals of like PegaSys is to maintain and scale Ethereum, and also to lower the barriers to entry to like Ethereum specifically for enterprises. So we have like 3 pillars. One of them is like product. We already have like a mainnet client, Pantheon, running. And then we have an R&D side where we work on Ethereum 2.2 implementation, as well as privacy and side chains. And then we also have a standard side where we push for like better open standards for privacy permissioning, especially with like enterprise Ethereum alliance, so that like it's easier for like companies to come in and join Ethereum. So let's move on to the next slide, please. So Artemis is our scalable and extensible Ethereum 2.0 client. It has a microservice architecture to allow distributed deployment and easy load balancing. It's enterprise friendly due to its permissive Apache 2.0 license and the fact that it's written in Java. Also, it's future proof because it's the only team with a current live Ethereum 1.0 client that has a team dedicated to implementing Ethereum 2.0 as well. And it's highly performant because we've always been building it with a focus on modular architecture and performance in mind. So to talk about the team on the next slide. Our team lead is John Ray in the middle. He has like experience ranging from aerospace to data science and mission critical software, and he's overseeing the project. Steven Schroeder on the right top, he has background in security and like mainframes, and he's focusing on testing and serialization. Shahan on the bottom right is one of the actually co-founders of PegaSys, and he's currently just joined like our team 2 weeks ago, and he's focusing on our P2P JVM implementation. Joe DeLong on the bottom left, he has extensive research in blockchain research, more than 3 years, and he's focusing on our Ethereum 1.0 integration and currently testing. Me on the top left, I've been working on state transition, validator client, and currently working with Steven on serialization stuff. If there are any questions about Artemis, I'm very open to answer them. Thank you.
Thanks, Jim. Yeah, we'll take those questions as they come. I think next we have Preston, who's going to talk a little bit about Prysmatic Labs and Prism. Preston, can you hear me?
Hey, I'm here.
Yeah.
Great. You guys can hear me all right?
Perfect. Thank you.
Perfect. All right. So Prysmatic Labs, we're an independent team only focused on working on Ethereum 2.0. Raul, Jordan, and I, the first two people on the top left there, founded this team at the beginning of 2018 based on there was a wiki article on GitHub that's talked about sharding, and we were all thinking, how do we get involved and make sharding happen and get Ethereum scaling, get Ethereum to scale faster? So we all met online on various chat rooms and through email and said, hey, let's just start working on this just for fun. And over the last year and a half, a year and a half now, it's really grown into a full-size team. We have 6 people now working on this project. We've had, this number is actually a little outdated. We've had over 50 open source contributors bringing onto the project different variety of expertise. Well, let's talk a little bit about our client, Prism. So we could go to the next slide. Prism is ETH2 client written in Go programming language. And what we're targeting are highly available production-ready deployments. So what that means is we're utilizing a client and server architecture where you have the bulk of the work put into a server called the beacon node. And then you have the client, which is the actual validator. And to stay highly available, you would want to run, multiple beacon chain deployments in your infrastructure. So that's something we've been targeting from day one. Is we want to have high uptime guarantees with a highly available configuration. And the next most important thing for us is really visibility on what's going on inside your client. If you're running these in a distributed fashion, it's kind of hard to follow logs and get good visualization from all of that. So we're adding in metrics first. So we have instrumentation as part of the binaries. If you're interested in that, kind of seeing, where where is most of the time spent in the code, and how can that be improved upon? That's automatically baked in with the client. And going forward, our philosophy with writing this code is that we're a very design-driven approach. So when we see the spec from the research team, we'll take it and parse it and then kind of come up with our own design spec on how we're going to implement this. And what we end up with is something that's very well tested. So we have, unit tests on all the core logic. Everything's really well documented as a result, and just the code is really easy to read and understand. And we're at less of risk of bug slipping in that way. And then our final feature here is that we are optimizing the client for performance, as well as ease of access for data access. So we have an API where you can query against historical data. So asking, what happened in Epoch 10, and sort of rebuild an image for your analytical tools or block explorers. And that's me. That's Prism. If you have any questions, write those in the chat or send them to Trent. We'll answer at the end. Thanks.
Thank you so much, Preston, and thank you for all the standing points. I think it's going to make my job in the next few slides easier. So we're going to move a little bit into a different discussion. We're going to talk a little bit about blockchain networking. We're going to talk about the challenges of Ethereum 2. I think you heard in the last 10 minutes that there's a lot of challenges related to the sheer performance numbers that we're trying to reach for. So let's go and talk a little bit about that. And we're still ahead of us. We have a demo of Genesis with ETH2, and then we'll open up for questions. So, the audience here is probably very savvy, but I think it's a good idea to also just talk about in general about blockchain networking. We're probably used to the old paradigm of client and server, where the server is well known, clients can connect to them using a reliable network connection. In blockchain, you get none of that safety. Now, clients are also servers, and we're now in a peer-to-peer network situation. So the unique challenges of blockchain networking is first to do a peer discovery, where you can find the other peers that are exposing the same chain that you're looking for. To have security throughout, from handshake to encryption, to securing the network layer, but also checking that you get cryptographic proof of the data that you receive. So you're not being fed bad blocks or bad transactions that may actually create adverse reactions to the rest of the network. And we want to also have a fast propagation time for blocks, for attestations, for any elements which are essential to the consensus mechanism. So far in the blockchain space, we've seen a few use cases which have been leveraged heavily by the different blockchains. The first one is, of course, to have a set of boot nodes that are always running, and they're statically assigned IPs, and they allow kind of an entrance door to the rest of the nodes I want to connect, at least initially. To supplement those nodes so that they can scale further than themselves, we use what we call distributed hash table that allows others to connect to a set of peers, ask for more information from some of the nodes that they know about, and to download a portion of a global hash table of all the peers available on the network. So this gives a resilience to the global network and allows avoiding situations where the network could be split into smaller pieces. For every, as I mentioned, for every block, every piece of data that is being transited over the network, you would want to make cryptographic verifications of everything that you receive, be it by signing it with a key, but also just checking that this block has been verified against the previous block and that there is a match in the chain. Finally, and this we'll talk about a little bit today, I hope, there are a lot of strategies around gossiping and syncing data. Some of the most novel ones have been tried with the ETH1 chain. Here we're going to talk about the approach we're taking with Ethereum 2, and this is going to be our next slide. So in Ethereum 2 networking, we have a unique need to do discovery And since we have the presence of shards, we will need to have different groups that will need to autonomously discover each other using the same distributed hash table. So for that reason, we're contemplating using Discovery v5, which has been developed by Felix Lange from the Ethereum Foundation. Discovery v5 allows nodes to broadcast topics and to broadcast capabilities that they are able to perform, which would allow self-organization of the nodes on top of a common mesh of networks. We also are working on those sync algorithms. So right now we want to make sure that we want to be able to sync really quickly. We have to be able to sync within block time. I know that the current block time is considered to be 6 seconds, and that's something that we are discussing to see if we can change that over time. We also have work with validators. Validators run next to the chain itself and are performing votes. And it must happen between inside a block time so that we can get votes in time. A challenge that's really unique to Ethereum too, I think, is that we have 9 different client teams and all different stages of standardization and productization of the clients, but they all come from different perspectives with very different needs. Some of them are, as we've seen, written in Go. Some of them are more enterprise friendly, written in Java. We also see some of those efforts being built towards mobile or very specific setups for embedded devices and systems. So as a result, the implementers and the researchers have chosen to standardize the network stack on libp2p, which is a complex set of framework for networking. This is maintained by Protocol Labs, the makers of IPFS and Filecoin. libp2p itself is a modular stack, so we can still decide a little bit what type of components we want to involve. So for example, here we have, in terms of handshake, a choice between Sekaio, noise, or TLS 1.3. Those choices need to be made based on the availability of those components in those different languages and to make sure that we're able to move at a comfortable pace towards implementation. Last but not least, we have to actually agree on a number of common set of messages. So the protocol itself needs to lend itself to all those syncing strategies and all those business needs of the consensus algorithm, so we can perform relatively short amount of time synchronization between clients, from propagation to catching up the chain. All those things need to happen using those messages. So there's something that is pretty hot right now. Let's talk a little bit about also the light clients. Light clients are something that are dear to Vitalik, and I hope I can grill him a little bit in the Q&A session about that. When Ethereum 2 was announced, Vitalik went to create a new way to standardize and serialize block data using specification called simple serialize. It's a very simple byte representation that allows a deterministic byte representation of any piece of data, meaning that you are actually able to say that a certain index, a portion of the block data is going to be forming from that element. That allows you, using a Merkle tree, to create a proof where you would be able to check that a portion of the block is present in the block just by knowing which index it is at in the block. So we can actually now create very light clients that can just gossip all those proofs and would allow us to make sure that cryptographically we are securely passing around a portion of the block that is important to us as part of this. So as part of that, so now we have the ability to create a new network protocol for light clients, and we have the ability to create light clients in general for Ethereum 2 that will have a much lesser computation overhead, and we'll be able to send simpler messages. So we'll be able to very quickly generalize a lot of the Ethereum 2 chain using this approach. So I hope that we will get to talk a little bit more about that. Now, one thing that we've been working hard at is to make sure that all the clients are able to talk to each other and that we're able to hammer out all the network needs that we've had. And one thing that is for sure needed is to make sure that we are able to communicate clearly between those client teams. So that might require, sometimes we have more communication. We use Discord, we use Telegram. We've been using Gitter as well. We also have regular meetings, and we have meetings in Meetspace to make sure that we're able to meet face-to-face, know each other, create kind of a collaborative approach to how we're working. This is not different from any open source project. It's a massive effort across the planet. In terms of how we go about it, we try to simplify the problem of creating a complete blockchain to simple tests that we can operate with in an isolated fashion. One of those tests that we started with was what we call the cold start, and it's now present on the ETH2 PM repository. So the researchers, the implementers came together and decided how they're going to simulate an ETH2 Genesis event so we can actually make sure that all the clients start at the same time, are able to gossip blocks, are able to come to consensus, and get the same blocks across. We also have a set of tests and a set of strategies which are being etched right now by different teams on syncing client with a running testnet. So we would start a testnet, it would go on for a couple of minutes, and then we'd be able to have another client start up, catch up with the testnet, request data as it comes up, and we're able to do a couple of strategies. The first one is kind of a simple strategy in the first test that we'd be running is a simple full sync where you keep asking for new blocks until you catch up with the chain. Another one that we might want to look at is to have another strategy where we use the finalization of ETH2, so you don't have to catch up to the whole chain. You can also just request the latest finalized block and kind of go from there a little bit while you catch up with the rest of the chain in parallel. Finally, and probably one of the crispier aspects of this is to have the right gossiping strategy. So I hope we get talk about that a little bit. Right now we use Gossip Sub from P2P. It comes with a set of assumptions and variables. I heard from Preston that we might be able to kind of change those variables, see how things fare. We want to make sure that we get the maximum throughput out of this gossiping strategy without flooding the network. So we're going to now show you a little bit of a demo of Genesis with an ETH2 client, Artemis. We're going to show you how Genesis can be of help for an ETH2 client as we are going to try to test as much as possible a real network out there on the internet. So here it is. So we're going to start building an Artemis client. We're going to get 10 nodes for it. We're not setting any limits. We're going to have 4 validators per node. Now we're sending that build context to Whiteblock. And then what we're doing is we're starting 10 different nodes of Artemis in different geographical locations, such as each of them gets their own VLAN, their own isolated network. That allows us to create as if a node was in Japan, another node was in Paris. We also provision the nodes with accounts. We add funds. So everything is already ready to go by the end of the build. Now, we can see the nodes as they go. We can see their utilization. We can see how fast they are. We can see if they're started correctly, all this good stuff. What we want to see also is kind of the log, how things are going inside that node. So here we can actually see how things are going, but we can also attach ourselves to that log so we can see how it's going over time. I mentioned this before. One of the core features of Genesis is to manipulate the network. So here we're going to show you how we can change, add some delay and change the bandwidth for the whole network. Now you can see here, we're going to just test that with a ping, and you can see that we added 10 milliseconds, and this exactly is being reflected here. You can also test that with an iperf command that showcases the bandwidth. Now, of course, these are interactive tests, and at any point in time, you may want to go back and clear those up so you can start again. We can also do a little nifty thing where we can cut the connection between two nodes specifically. Now you can see here, we just cut the connection between node 0 and node 1. And now if you try to ping between those two, it won't work anymore. At any point in time, I can also decide to uncut that connection and get it back. So that's impressive. But on top of that, we can now also partition the network so we can actually create a real rift between different nodes of the network. So now we're going to isolate node 0 and node 1 into their own partition. There we go, we got a success for that. You can still see that the pinging works. But if we try to ping from node 1 to 2, for example, we see a big empty void. Same thing with 0 to 2. At any point in time, we can choose to reconcile this network. And there you go, it's working again. So some of the instrumentation we allow also is based on the ability for us to interface with the software running inside the nodes. And for that, we allow you to SSH directly inside the node itself in its software. So you can actually see how things are going inside. You can see this, every file, everything is available to you. You can perform all sorts of tooling and testing inside the node itself. But that's not good enough, because sometimes you'll be running this without the help of an operator. So if you were to do that using, for example, Jenkins, you might want to be able to run PSAUX from the outside and get that output right away. And there we see here Artemis, the whole class path Java here. And that is pretty much it for demo. So I promised that we'll have plenty of time for Q&A. And oops. And this is exactly what we're going to do now. I know Trent has been collecting a lot of questions from our participants, and I'd love it if we could get started on those questions. Trent, are you here?
Sure, yeah. Can you hear me?
Absolutely, yeah.
Great, yeah. So we had originally gotten some questions through email, so I'll start with those. The first one is somebody's asking how you can, what sort of outputs you can run with Genesis platform, and like what you can actually do with the data that you're getting from the logs. Like, why is it useful?
Right. So this short demo is showcasing a little bit like what you would do in terms of testing, how it can play out with an operator. One thing it's not showing, we have another demo for that that's available on YouTube, is that you can also export all the data that has been collected as part of the run. So you can actually test and get the data that each of the 10 nodes, for example, here we're collecting. We collect log data, we collect block data, we can collect even more data as needed. We can, for example, interface with Prometheus, get metrics, all this good stuff. And we make it available to you using the CLI, so you can actually download that data down to your laptop and perform all sorts of analytics. We also have the ability to interface this data with Jupyter notebooks, so you can perform all sorts of advanced analytics, parse the logs. We recently did this with Geth, where we were able to get the block propagation times by parsing logs and comparing with the timestamp of a particular block. So all this is available to you. Yeah, this demo does not show that, but we have the ability to do that, and you can see it on YouTube.
Great. Another question, is Genesis only for testing blockchains, or can it do other more distributed systems type testing?
Very good question. So the unit of compute that is required to interface with Genesis is a Docker image. We actually do not really care, as long as you're exposing network conditions, network between the different nodes, we will be able to satisfy that, and we can create any sort of complex distributed networks. We can create geographical replication, for example. So we can be a good test bench, for example, for a Cassandra cluster, a Kafka cluster, even just a RabbitMQ replication cluster, depending on the needs of the enterprise. So we also have been looking at getting more involved into IoT use cases, especially as we will need to simulate the number of devices at the edge and a number of queues. So all those use cases are in our that are things that we support at this time.
Awesome. So I think this next one probably is best answered by either Preston or Vitalik, and I'll just read it off. Standardized network messages seem crucial for implementing phase zero in multiple clients. Why is network messages not a part of the phase zero spec, and does it have its own upcoming spec?
There is a document that contains standards for those things, right?
Yeah, that's a new thing that came out last week, I think. The networking spec, the new one, does have message types defined, and they're all SSD encoded messages right at this time.
Mm-hmm. Yeah, I mean, I definitely support considering integrating that more closely into the rest of the spec. Mm.
But yeah, it's just being developed in a separate document, right?
Yeah.
Yeah, it's on the same repository, so you should be able to find it. And the second part of the question, I think, was why is this important? And that's because in order for it to have a true multi-client testnet, messages need to be compatible, encoding, decoding, the formats, the data structures all need to be the same to have that compatibility. So we have been working on that recently. That's sort of like the most recent update in the specs repository in terms of phase zero stuff, as far as I know.
Great. So another general question, if somebody wanted to test some hypothesis, what specific things could they do? And maybe this is directed at Antoine, but how could they use Genesis to test specific assumptions about network capacity or something?
Oh, yeah. So I think this is something that we answer very generically when we discover clients what they want. We have a methodology by which we take them through a series of tests, and we have a test plan approach to everything we do. So I'll give you an example, but it really is something that we work in collaboration with people as they come to us. A good example would be that usually what they have is there a brand new blockchain, in which case what they want to see is degradation of a real network traffic. So for example, we start with a control group with no problems whatsoever, and then we make it worse and worse and worse by just applying factors of noise and bandwidth limitation until we reach kind of abysmal quality conditions. Some folks come to us now with much more mature solutions which have been in production for a while. We had this case, for example, recently where people came to us with wanted to change GEF ever so slightly and asked us for a variation of that GEF client, right? So we were able to test and actually benchmark one against the other so we could tell them, confidently what was going on there. A key point of that was we had to test it with a mainnet state. So we are now supporting the ability for folks to test it with the actual Ethereum mainnet state as part of a isolated setup, which gives folks a very comfortable feeling. We can repeat those tests. We can really make it easy on them. They're really comfortable then pushing those results and making use of them.
Let's see, the next question. Is there a write-up on the process of gossiping data over SSE via Merkle proofs?
That's a question for Vitalik, I think.
Was that gossiping SSE via Merkle proofs?
Gossiping data over SSE via Merkle proofs.
Right. I guess what's the specific problem that you're trying to solve there? Because for example, there's going to be some cases where a client needs some specific piece of data, and then for that you would provide an SSE Merkle multi-proof and those network messages, or are we talking about something else?
Not sure. If there's anything unresolved from our Q&A here, we can just go to the Whiteblock Telegram, and if people have continued questions after this, we can get a little bit more in depth there. Let's see. A question about Prism. How does Prism plan to use Genesis and its relationship to how they might test Gossip Sub?
Yeah, that's a great question. What we want to do is figure out how the performance changes between different configurations with Gossip Sub. So there are a lot of parameters that define the algorithm on how messages should be relayed once you've received a message. How many peers do you send it to, and what the like heartbeat timeout and things like that. We'd really like to see that we've already landed on the ideal parameters for that for the network of the size we're expecting. And also, it would further give evidence to the 6-second block time if we're able to propagate fully to the edge of the network. We think we can understand this kind of logic in a framework like Whiteblock with their analytics and data collection. One more thing we would like to see is the CPU and memory performance trade-offs of adding something like a snappy compression to the networking protocol to see, is the trade-off in bandwidth worth the trade-off in computing and resources. So we have a couple experiments we want to run in the next couple of months, and we're really looking forward to it.
Awesome. Next question is for the Artemis attendees, and they're wondering if there's been any fuzz testing on the ETH2 implementation.
I don't know about what has been done on the Whiteblock side, but we haven't started testing fuzz testing on Artemis yet.
Was there anything that you've done to set up the client to make that easier, or what steps has your team taken to prepare for that in the future?
What steps we have taken to prepare that in the future?
Yeah, what's your general testing? Do you guys do any local testing, or is it something that's going to happen later with the interop?
Yeah, we have a couple forms of tests. One of them is our own unit tests of everything from state transition functions to SSC unit tests, and then we have our integration test where we run one node to n nodes and see if we get any errors during running a beacon chain from start or from starting from some specific point. And then we also comply with the Ethereum reference test, which all other clients are working with as well.
Awesome, thanks. Let me just check. There was a question about Gossip Sub parameters and how we can actually test what they are, and whether the hard-coded parameters are going to work for what ETH2 is trying to accomplish.
Hey, I touched on that briefly, but yeah, we want to be certain that the parameters that are defined in the networking spec and defined default parameters for Gossip Sub are going to propagate effectively through the whole network. So that's an experiment we'll want to run on the Whiteblock.
Cool, thanks. This is a bit of a more general question for Vitalik. The question is, why are there 1024 shards, and is that number expected to change after phase 3?
Why are there 1024 shards? Basically, the general idea behind picking that number was to try to balance between the load of the beacon chain and the load of a single shard, which are the two kind of natural constraints on the size of a quadratic sharded system. So, for example, we could have achieved the same scalability if the beacon chain was had 10,000 shards, but each shard was 10 times smaller. But then, like, there would be an imbalance because the sharded system would, or because each shard would be really easy to process, but on the other hand, the beacon chain would take a hugely powerful computer to stay in touch with. And on the other extreme, if we had 10 shards, but every shard was incredibly big, then the beacon chain could be processed really easily, but the shards would be really huge. So the goal of the calculation is to basically try to equalize the two, because that's the point at which we can maximize the total scalability of the system and if subject to some particular constraint on the load that we can impose on any specific computer.
Great, thanks. Next question, probably also for you, Vitalik. A while back, I heard that ETH2 would be switching out the Merkle-Patricia tree for another data structure. Is this still the case? And if so, what's the new structure and what's the reason for this change?
Oh, good question. So I think plans there have been a bit derailed because of this execution environment pivot that's happened over the last few months. And basically the kind of primary thrust of the execution environment's pivot is that the protocol doesn't maintain a kind of layer one notion of large shard state. So there are small shard states, but they're not going to be larger than the size of a block. But inside of execution environments, like they are definitely going to end up implementing their own state schemes, and so they'll have to use some kind of data structure. So I've been doing some work over the on and off over the last year or so on optimizing sparse Merkle trees, and basically using binary trees with a slightly different hash function to create kind of theoretically optimal and very simple Merkle tree performance. So that's one direction that I think execution environments could end up taking, but they could also end up designing, going in a different direction. Like you could have one do some kind of binary AVL tree. You could have one just use some totally different kind of accumulator or whatever else.
Great. Next question. What are the trade-offs with choosing a fixed shard number? And could that possibly be increased or decreased in the future as demand changes?
Yeah. So the main challenge is that from inside of a blockchain protocol, it's extremely hard to measure the level of demand. And like one of the challenges, for example, is that in a mature economy, we can expect there to be a huge amount of demand for using the blockchain in extremely trivial ways. So, for example, if the demand for putting data in the blockchain starts falling towards zero, eventually transaction fees will become low enough that people will just start using the blockchain as a place to put encrypted backups of their hard drive, and that's incredibly inefficient. But if no other use cases exist, then those kinds of use cases will just start popping up and dominating. And so you can expect to see an equilibrium where like the chain is full or close to full, like, regardless of what level it's at. And there is this kind of approximate level of fees that's being paid, and those fees are denominated in Ether. But if the fees denominated in Ether go up by a factor of 10, is that because demand went up, or is that because the price of Ether went down by a factor of 10, or is that a combination of both? So from inside the protocol, it's just really hard to figure out like what the right shard count or even what the right block size for a single shard should be. So that's the main reason why we've gone with this fixed approach for now. But like if it's kind of decided that it's a good idea to just manually increase the shard count at some point in the future, then I think that's definitely something that could just be done with a hard fork.
Gotcha. All right. Looks like we'll do one last question, and then Antoine will wrap up. Which ETH2 clients will Genesis be able to test against? Was it only Prism and Artemis, or will there be others?
That a question about Genesis?
Yeah.
We are completely client agnostic in the way that as long as you're speaking Ethereum 2, we will be able to run you. We just need a Docker image that enables us to configure the client and make it run as part of the network. Ideally, what we want to do in a matter of weeks or months is to get to a point where we can actually run testnets with the 9 different clients embedded into a testnet and see how we can pretty much replicate the tests that we run now with just 1 or 2 clients with the vast majority of clients at once. So we can ensure that everything works out of the box.
Great. There's a couple more questions, and I'll try to transfer them over to the Whiteblock Telegram. But if we didn't answer your questions fully, or you weren't able to join us for the whole talk, this has been recorded, and we'll be releasing it on the Whiteblock YouTube channel. So if you weren't able to attend, or you want to refer the video to somebody else, you can pass that along to them. But Antoine, if you want to wrap up, go ahead.
And thanks, Trent. And then, of course, if you'd like to get involved and you'd like to have a look, ETH2 is an open source effort. It's available here on GitHub. You can see the specs here. The Artemis team always likes patches. You can go see them on the PegaSys engine Artemis. I recommend, of course, that you get in touch with Prism if you're interested in Go coding. Don't be shy. Also join the Discord. They are very friendly folks. And if you have any interest in Genesis, our code's actually open source. You can take a look under this repo. As for me, Antoine, CTO at Whiteblock, you can here get my email, my Twitter, my Telegram handle. Don't hesitate to get in touch. As Trent mentioned, we have a Whiteblock community on Telegram. You can get there. You can ask any questions you like. We'll try to run through a series of sessions as well there. So thank you so much. I'd like to thank the panelists, Vitalik, Preston, James. Thank you so much for helping out and run this webinar. It's been a pleasure to host you all. I hope to see you again soon. Thanks, everybody.